Welcome back, everyone. Welcome to the last session of today's day. And here we are going to start with our next part of the energy chapter, and this is nuclear energy. Now, looking at nuclear energy, the structure of our chapter would be basically divided into two parts. The first part will be more of nuclear science, understanding the basics of nuclear energy and how exactly do we get this energy, in what form do we get this energy, and what are the various ways in which we get this energy. The second part of our discussion will be more about nuclear technology, where we'll understand a bit about what is nuclear fission, what is nuclear fusion, what are nuclear reactors, what are the applications of nuclear energy, and these are the areas that we are going to discuss in the second part. So the first part is more about nuclear science and the second part is more about nuclear technology, and this is what we are going to discuss in this particular part. So first and foremost, to start with, try to understand the meaning of this word nuclear energy. What do we mean by nuclear energy? Now, nuclear, the word comes from nucleus. Nuclear is being used because this is an energy that we are deriving from inside the nucleus, and hence we are saying that this is nuclear energy. All right, that's why we are saying that this is nuclear energy. So now when it comes to the nucleus, just understand how exactly are we looking at the nucleus. So inside the nucleus, what we see is that first and foremost, even before going to the nucleus, let me tell you how exactly do we see the structure of an atom. So let me start with some of the basics here so that you'll understand where the source of energy actually is. Now, overall, what you know about the atom first. We know that atom constitutes of electrons, protons, and neutrons, correct? Where if you look at the structure of atom, what we understand about the structure of atom is that this is a typical shape of an atom, that where you have all the electrons in various different orbits, and at the center you have a very small part, and this small part is called as the nucleus. Inside the nucleus you have protons and you have neutrons. All right, so protons and neutrons inside the nucleus, and then after that there are various shells in which you have all these electrons. So this is a typical shape of any given atom. Now, when you go back into the history of our understanding of the atom, it was not always well understood that how exactly atom is. If you look at the early theories of atomic structure, we will find that initially it was believed that atom is the smallest indestructible part of an atom. Sorry, of matter, meaning that atom is indestructible. You cannot break down atoms. This was the early belief. This was the early theory of atomic structure. But then we see that slowly and steadily, as the science also started to evolve, we understood that this was not exactly correct. We can't say that atom is indestructible. There was a particle that was found inside the atom which was named as electrons. So first, if you have heard of it, there was Dalton's atomic theory, and Dalton's atomic theory simply said that atom is completely indestructible. But then came J.J. Thomson, and J.J. Thomson proved that there is something called as an electron. So he presented a model of an atom which had electrons, but he did not say anything about any protons or any structure as such. His structure was very similar to how a watermelon looks like. That if you see a watermelon, you have the reddish part. For him, the reddish part was the positive sphere, and the seeds that you have embedded in this watermelon, these seeds basically are nothing but the electrons. So we have electrons like this, and in a manner you can say that this led to the discovery of electrons. That initially it was believed that atom is indestructible, but then we were able to discover electrons. So this was J.J. Thomson. After J.J. Thomson, we see that another discovery happened, and this discovery was discovery of a proton, and this discovery was done by Rutherford. So there was a scientist called as Ernst Rutherford. When he was doing his experiments, he found that there must be a small part of the atom which contains all the protons. So in his experiments, he basically defined protons. Although independently, it is also said that there is another scientist who should also be given the credit for discovering protons, because he had discovered positively charged particles. He did not typically discover what you can say proton is, but he actually still he discovered some positively charged particles, and this scientist was Goldstein. So Goldstein and Rutherford both independently proved the existence of positively charged particles, although it was Rutherford who provided a formal name to proton. So discovery of electron had happened, now discovery of proton happens. And then after that we see that ultimately discovery of a neutron also happens, and this was James Chadwick. James Chadwick finally found that there is a neutral atom also, and this neutral atom neutral matter or neutral particle as well, and this neutral particle was named as neutron. So how exactly are we defining? Just let's try to understand this. So first and foremost we are saying that the early atomic theory, all right, the early, just giving you a brief about the history, the early atomic theory says that atom is indestructible. Atom is indestructible, cannot be broken. Then after that we have J.J. Thomson. So J.J. Thomson basically he sorry so he discovered electrons. So here discovery of electrons happened. Then after that you have, so he only discovered electrons, and in a model, this model was called as plum pudding model, and it looks like a pudding, and similarly you can say that even as like a watermelon. Now after this you have Rutherford. This is where discovery of protons is done. Discovery of protons. So this is basically done by Ernst Rutherford, and simultaneously there was Goldstein as well. He also discovered positively charged particles. Positively charged particles. All right. So in this scenario, discovery of protons happened. Still, neutrons were not discovered. And then we see that there was this new discovery that was done by James Chadwick. This was done by James Chadwick, and he was even given a Nobel Prize for this. So discovery of neutrons happened here. And then lastly, we see that there is the Bohr's model. So ultimately, there is the Bohr's model, or the new model of atom. And then after that, there is a quantum model of atom also, but we'll not go there. So in this manner, we see that this is a brief history of what basically we saw happening over a course of time. So here, this was also called as Dalton's atomic theory. This was Dalton's atomic theory. So this is how we see that one by one, slowly and steadily, we kept on uh, seeing or discovering new terms or new particles. So overall, typically, as of now, what we know of is this, that you have all these electrons which are there in electron orbits, or also called as shells. Then after that, this part, the mid part of any given atom, which has all the protons and neutrons, this is called as the nucleus. This is called as the nucleus. And then you have the protons and also the neutrons. You also have the neutrons. So that's why these are the particles that we have inside the atom. Now, one thing For a very long time, actually, we just believed that, okay, fine, there are protons and there are electrons. And we did not know that there is a third particle as well called as the neutron. And this discovery of neutron, that basically was done by James Chadwick, the basis for that also developed when we started understanding what we mean by something called as an isotope. That when we look at the masses of the nuclei of hydrogen, we see that the nuclei of hydrogen have masses in the ratio 1 is to 2 is to 3. All right, 1 is to 2 is to 3. Now, this ratio of 1 is to 2 is to 3, what we basically see in this particular scenario is that this basically is where there was some confusion in the minds of the scientists, that if you have only protons and only protons and electrons, how is it possible that there is an extra mass? Because if it was, let's say, extra proton or extra electrons, then in that case they should be charged particles. Correct. Extra proton. For hydrogen, what do we know? That there is one proton and one electron. So if there is only one proton and one electron, but the masses are in the ratio of 1 is to 2 is to 3, then it certainly means that there must be something else apart from protons and electrons which is adding to that extra mass. And this is where the discovery of neutron, or the base for the discovery of neutron, actually was set up. So this is a concept where we also call this as an isotope. This is the concept of an isotope. Anyone who can tell me first, what do we mean by an isotope before going further? What do we mean by an isotope? Before discovery, neutron was dark matter. Wonderfully put, Saurav. You can say that. Elements having same atomic number but different mass number. Perfectly correct. Perfectly correct. So what we are saying is that isotope basically, uh, we are saying that here we have same atomic number but different mass number. Same atomic number, different mass number. Atoms of the same element with same atomic number but different mass number. Now, what is atomic number and what is mass number? What do we mean by atomic number and what do we mean by mass number? Yes, atomic number is equal to the number of protons. So atomic number is what? It is number of protons. Number of protons. What do we mean by mass number? What do we mean by mass number? Yes, equal to the sum of protons and neutrons. Number of protons plus neutrons. So these are called as isotopes. Okay, one more question for you. Can we say, can we define, all right? Listen to the question carefully. Can we define atomic number as number of electrons? Okay, let's let's do a small poll. That I'll just give you 10 seconds to answer this. Can I say that isotope, that atomic number, what I'm asking is, can atomic number be said to be number of electrons? Can we define it as number of electrons? Choose A for yes and choose B for no. All right, quickly, I'll just give you 10 seconds for this poll. Can we define number, atomic number as number of electrons? Okay, so 64% of you have said yes and 36% of you have said no. I'll tell you why the answer should be no. I said, can we define it as? Definition wise, number of protons will always be the definition of an atomic number. Although in a neutral atom, we understand that number of protons and number of electrons are equal. So then in that case, it can also be equal to number of electrons, but we cannot define it as number of electrons. Understand the difference between these two things. We cannot define it as number of electrons. We can say that it is also equal to, it can also be equal to number of electrons. Understand why? Because number of protons defines an element. All right. We say that atomic number is the most unique feature of any given element. If you increase or decrease the number of protons, the element itself changes. But that doesn't happen if you change the number of electrons. An element might lose an electron or maybe gain a couple of electrons and become positively or negatively charged. Correct? But that doesn't define uh, a change in the element. It just defines that some electrons have been lost or gained. But if you lose or gain a proton, then the element itself changes. That's why number of protons is the most intrinsic property of any given element. All right. I hope you understand this. That why I say that we can't define. So I would choose B, because I would say that we cannot define atomic number as number of electrons, because electrons can be gained or lost, but protons can't be. If you lose or gain the proton, it changes the element itself. But that doesn't happen if you lose or gain an electron. So hence, if it has to be defined, we'll say that it is defined as the number of protons. Clear? All right. So this is what isotope is, and in these cases that we see, these are the isotopes of hydrogen. So basically being hydrogen, deuterium, and tritium. And while we represent it, as one of you had also mentioned, I think Gulam, you had mentioned that if or if we represent this as something like this: 1H1, 1H2, and 1H3. So this basically 1 is atomic number. This is atomic number, meaning that the number of protons is 1. This basically is the mass number. This is the mass number, meaning that this is protons plus neutrons. So that's why 1 plus 0. In this scenario, again, this means that there is one proton, and this 2 means that there is one proton and one neutron, because number of protons will not change, most intrinsic property of an element. So here this 1 means that number of protons is 1, and this 3 means that number of protons is 1 and number of neutrons is 2. All right. So this is how we define the given isotopes of hydrogen, and this in a manner you can say that it led to the discovery of neutron. So all these things that I'm discussing, please take sit here with some concentration, because some of these concepts that we are dealing with, it might become a little difficult for you to understand at times. So I just want your focus. If you have any doubts whatsoever with regards to whatever we are discussing, keep asking your questions. All right, keep asking the questions whenever you feel that you are not able to understand something. Please do that, because some of these concepts that we learn over the course of next 1 hour or so, it perhaps will be a little difficult. So that's why try to be here with complete focus as much as possible. All right. So until now, what do we know? Just a quick summary. That first we thought atom is indestructible, then we discovered electron, then we discovered proton, then we discovered neutron. And today what we understand about an atom is that atom has all these electrons in perfectly circular orbits around a very central small part, which is called as the nucleus. And inside the nucleus we have protons and neutrons. And when it comes to any given element, the most important property of any element is the number of protons that it has. It cannot change. Number of neutrons and electrons could change. So this is basically what we know. So discovery of neutron happened. Now in a manner you can say that the atom was complete for us. All right, now this atom was complete, that we knew that okay fine, these are the most important particles that we have inside the atom. Now next, there is one very very important concept, and this is also a concept related to some confusion that many scientists also had during the early course of discovery and the studies and research that used to happen in nuclear energy, or look, you can say in a manner, the study of an atom. So what the scientists saw was they saw that there was a problem. What this problem was, according to them, what the problem was, that something that they had named as mass defect. So understand what according to them the problem was, that let's say you have an atom, all right? Let's say you have an atom, and this atom has one proton and one neutron. All right, it has one proton and one neutron. Suppose, all right, just as an example, obviously these are not true numbers. Let's say the proton weighs 10 grams and neutron also weighs 10 grams. So then in total, the atomic weight here should be 20 grams, right? It should be 20 grams. But what they found was that this atom does not have the mass of 20 grams, but rather, let's say it's 15 grams. So it should have been 20 grams, but it actually is 15 grams. So they did not understand what was happening. And why is the atom losing this mass? Although there still is one proton and one neutron. So where is this mass going? Let's say instead of 20, it was 25. Instead of 20, if it was 25, then you would have said that, okay, fine, maybe there is something extra that I'm not able to see, and that is bringing 5 extra grams. Completely fine. But when you know that only this 10 gram and only this 10 gram is there inside this nucleus, then how is it possible that the mass is not 20 gram but rather 15 grams or 16 grams? So this they did not understand. The early research and study could not comprehend why something like this was happening, and very conveniently this was named as mass defect. That something is wrong with the mass of this nucleus itself, which is leading to this kind of a discrepancy. So that's why the nuclear mass, which was found to be always less than the mass of neutrons and protons, this was named as mass defect. All right, this was named as mass defect. So this was basically what they understood, that fine, okay, there is something that we probably are missing, but whatever it is, there is some kind of defect which is leading to decrease in mass. But then came a scientist whose names we will be taking in every given chapter. And this was again Albert Einstein. Albert Einstein, through his theory of special relativity, gave a very important equation. An equation that I'm very sure that all of you have heard about. Whether you know the meaning or not doesn't matter, but you've heard about it. E is equal to mc squared. This is the equation that he had given, where these three terms, E, M, and C, what do they mean? E means energy, M stands for mass, and C stands for speed of light, which is 3 into 10 to the power of 8 meters per second. All right. So E stands for energy, M stands for mass, and C stands for speed of light. So through this equation, what Albert Einstein was able to explain was that mass should be considered as a form of energy. Mass should be considered as a form of energy, and there is an interrelationship between mass and energy. That for example, if you have, let's say, mass equal to 1 kg, suppose that we have mass of 1 kg, then the energy related to this mass of 1 kg in these particles will be 1 into 10 to the power 3 into 10 to the power of 8 squared, which is equal to 9 into 10 to the power of 16 joules of energy. So 1 kg of particle, 1 kg of particle, meaning let's say 1 kg of neutrons, is equal to 9 into 10 to the power of 16 joules of energy. Enormous amount of energy. So now the scientists understood that they have stumbled upon something great, that this atom, or rather this nucleus inside this atom, could be a reservoir of a huge amount of energy. A huge amount of energy, that there is a very huge amount of energy with which very strongly this nucleus tries to hold all the particles together. The particles meaning the protons and neutrons. The protons and neutrons which are inside this nucleus tries to bind this proton and neutron number with a very strong force, and thus a lot of energy, and this energy was named as nuclear binding energy. All right, this is called as nuclear binding energy. What do we mean by nuclear binding energy? The energy with which the nucleus is binding all the particles together. All right, the nucleus is binding all the particles together, meaning all the protons and neutrons together inside the nucleus. So that energy is called as nuclear binding energy. Fine. So this is what we know as of now. So nuclear binding energy basically was defined. So what we know is that nucleus is made of neutrons and protons. Therefore, it must be expected that the mass of nucleus is equal to the mass of individual protons and neutrons. However, the nuclear mass was found to be always less than this. This difference in mass of nucleus and its constituent is called as mass defect. So now from here on, what happened is, sorry, yeah, so from here on what happens is that we found that there is this nuclear binding energy, that the lost mass was basically getting converted into energy. Correct. This, the lost mass that we have here, I'll just write it down here. The lost mass gets converted into energy. The lost mass gets converted into energy. So equivalent of those 5 grams, all right, equivalent of those 5 grams, basically those 5 grams have converted into energy. Why? Because this is this energy that you require to bind everything together. All right, the nucleus requires this energy to bind everything together. That's why this mass basically is getting converted into energy, what we saw with theory of special relativity. So nuclear binding energy is the with which energy with which the nucleus binds its particles, basically the protons and neutrons, all right, strongly within itself. Strongly within itself. This is called as nuclear binding energy. All right, so this is basically where we get the idea of what nuclear energy is. This energy is nuclear energy. The force that corresponds to this energy is nuclear force. All right, just writing it out here. The force corresponding to this energy is called as, what we had discussed, if you remember, we discussed strong nuclear force. This is essentially the strong nuclear force. Remember last class we had talked about that there are 4 fundamental particles, right? Sorry, 4 fundamental forces: strong nuclear force, weak nuclear force, electromagnetic force, and gravitation. So this strong nuclear force basically comes from here. All right, strong nuclear force comes from here. Basically the force which is equivalent to that energy that is trying to bind everything together, this is the force. So we get the basics here. We understand the basics here, that okay, nucleus is a big reservoir of energy. Have you heard of this film? There is this movie that has released this week. I mean, just on Friday, there is this film released, Oppenheimer. Have you heard of it? Yeah, some of you already know about it. So basically, what I'm discussing here is the basis of the film. Is the basis of the film. So, in other words, I would say for more information, watch the movie, but avoid the movie for now. Focus on your studies, and then you will get a lot of time to watch the movie. So don't worry. So essentially you can say that all these things, they became the basis of everything that happened later, whether it is the atom bomb, whether it is the electricity through nuclear energy, These are the things that became the basis of all that. All right. So, so now these are few things that we know. Now the next thing that we need to also understand, just one, yeah, sorry. Hmm. The next thing what we also need to understand, so until now we understand the basis of this nuclear energy and the strong nuclear force. Now there is something else. When we look at the mass number versus energy of all the different elements, hydrogen, helium, oxygen, carbon, chlorine, bromine, iron, magnesium, whatever you think of, all right, all these elements, when we look at the energy content versus their mass number, here also we find something very interesting. What we see is that essentially when you start increasing the mass number, you see that there is an energy increase that happens. Correct? The binding energy keeps on increasing. The binding energy keeps on increasing as there is an increase in mass number. But at some point, it starts to become very constant, it very stable and constant. And for a very long time, it remains constant. All right, it remains constant over this value, 8 mega electron volts. It remains above this value of 8 mega electron volts. Now what we basically see is that above 8 mega electron volts, all right, above 8 mega electron volts, if any element has an energy above this 8 mega electron volts, then they are fairly stable. All right, they are fairly stable. So now, because they are stable, they are happy in life. I mean, this is what all of us want, stability in life. Now to gain that stability, all the others who are not in this zone, who are not in the zone of 8 mega electron volts, they would want to get there. All right, they would want to get there. Now there are two ways in which they can get. One is with basically the heavier element. With the heavier element, what we see is that their mass number is big. So what they understand is that if their mass number could decrease, if their mass number decreases, they go to this part. Correct? Uranium has a very large mass number. So if that mass number decreases, then it goes back into the area where it can have an energy level which is stable. So how can uranium do that, or any heavy element do that? By breaking. If they break down into two pieces, then both these pieces will perhaps lie in this range because the mass number would decrease. Mass number decreases, binding energy increases. So in this manner, this is something that would happen, that all of they would have to break. So if uranium breaks, it will again go back to its stable level. This is called as fission. This is what we call as fission. Because what is the meaning of fission? What is the dictionary meaning of fission? To break, right? The meaning of fission is nothing but to break. So what is happening? Uranium is breaking, and by breaking, it is coming back to the stable energy level. Now what about hydrogen? In case of hydrogen, it has very less atomic number and very less mass number, hence. So because it has very less mass number, if it has to go to higher energy level, it will have to combine. If it combines, it will be able to increase its energy. Correct? If it combines, it increases its energy. So what will it do? It will undergo fusion. What is the meaning of fusion? To join. The dictionary meaning of fusion is nothing but to join. So what happens? Two hydrogen nuclei would join together, fuse together, so that they can go to stability. This is basically essentially what everyone is trying. That, looking at a philosophical level, every one of us wants stability in life, and this stability in life is what hydrogen and uranium both are wanting to attain. So there are ways in which you can attain that stability. You would be told by your parents many a times that you get married, and when you get married, you will become stable. So getting married and becoming stable is like fusion, that two people combine their forces together to become more stable in life. So that's like marriage. And on the other hand, there is fission, the painful part, the breakups, the divorces. So that is what fission is. That when Because there are two people together, they have become unstable. Unfortunately, sometimes this happens, reality of life. And then they would have to separate, and that is fission. And by separating, perhaps they become stable in life. So this is where we see that this basically will happen, that in some cases there is fusion and there is some case where there is fission. Why fission? Because they have very large mass, they have to break so that they can come to the stability part. And on the other hand, we have hydrogen which is very small, so it needs to join forces to increase its mass number so that it can get to the stable level. Hence, the smaller elements, the smaller atoms would undergo fusion, and the larger atoms will undergo fission. Understood? I hope that this concept is clear. When do we get fission and when do we get fusion? Now there is one more concept, and this fusion, this concept is called as radioactivity. But before going there, I just want to understand if everything is clear. If you have any doubts, please ask your doubts here. One part we have completed about basic understanding of what atom, nucleus, and all these related concepts are. So if you have any doubts here. Wonderful. Wow, all clear, good. All right, so let me move forward. So the next topic for us is radioactivity. Now, there is, what we basically see is that whenever you have any unstable nucleus, when you have any unstable nucleus, the unstable nucleus undergoes something called as a decay, and this is called as radioactive decay. So when we say that this is an unstable nucleus, understand what we mean by unstable nucleus. Unstable nucleus, a nucleus can be unstable in two ways. One, when what we just discussed, when the number of protons is very high. When number of protons is very high, that is one kind of instability. The second kind of instability is when the number of protons, when the number of protons is not equal to, it's not, when it is not equal to the number of neutrons. This is also a case when it becomes unstable. All right, so one is when the number of protons is very high, and the second is when the number of protons and number of neutrons is unequal, basically producing a kind of an asymmetry, producing a kind of an asymmetry in any given atom. So in these two cases, we'll say that this is where we'll say that something is unstable. Now, in these two cases, we'll see that this, whenever these two things happen, it will mean that this is an unstable nucleus and it will undergo a decay so that it can again become stable. So how exactly? There are two ways in which we see this. First one is called as alpha decay. Right? We'll say that this is alpha decay. We can also write it as this. This is the sign. Similarly, this is beta decay, and this one is gamma decay. All right, alpha decay, beta decay, and gamma decay. So alpha, beta, and gamma. Now alpha decay will happen in the first case. All right, alpha decay will happen in the first case when the number of protons is very high. This is something that will happen. So when number of protons is very high, so this is where we'll see that something like this will take place. And beta decay will happen when the number of protons is not equal to the number of neutrons. So this is something that will happen in case of beta decay. And gamma decay is where some high amount of energy is is released. Usually accompanies usually accompanies alpha or beta decay. How exactly it accompanies alpha and beta decay, we'll discuss that later. All right. So these are the three ways in which instability in any given nucleus is taken care of. So first, for example, when we talk about alpha decay, in alpha decay, what we see is that the mass number of the product is 4 less than that of the decaying nucleus, whereas the atomic number is decreased by 2. So alpha decay will happen in a heavy nucleus. All right. Alpha decay will happen in heavy nucleus, and this will happen when number of protons is very high. So in this case, we'll see that some of the particles will come out. So if you see here, you have plutonium, and this plutonium will start losing particles. So that's why this is decreasing by 4 and this is decreasing by 2. Correct? So in this manner, plutonium is converting into uranium. So that's why what basically is being released is equivalent of the helium nucleus, 4He2. So when we are saying 4He2, tell me how many protons and how many neutrons? How many protons and how many neutrons when we say 4He2? Yes, 2 and 2, perfectly correct. So 2 protons and 2 neutrons. So basically plutonium is losing 2 protons and 2 neutrons, so that it converts into uranium, which is little more stable as compared to plutonium. So this is basically what will happen. Now, overall, basically alpha decay will happen in these kind of cases where we see that the number of particles is keeps on increasing. Understand the problem. All right, understand what exactly is happening here. Let's say okay, let's say that instead of an online class, let's say you are in an offline class, and this offline class has a capacity of 100 students, that it can accommodate 100 students. So let's say you are sitting right now in the classes, and you are, let's say, around 80 of you who are sitting in the class. Now, out of all of you who's sitting in the class, uh, the seating capacity is 100. There are 80 of you in the classroom. Imagine that all of you are protons. All right. So then you can accommodate. Fine. All right. You can accommodate because there are spaces available here. But then, let's say I don't want to teach in the early morning classes. So I ask the morning batch also to start coming and sitting in this particular classroom itself. So what happens, let's say there are some let's say 50 of them in the morning class. So what happens, all these 50 people will also start to try and shift to the same weekend class. What happens now? The seating capacity is 100, and we now have 130 students in the classroom. What happens next? Instability, right? Instability, you would not like it. You would say that we are the original owners of this classroom, you are not welcome here, and you try to just throw them out because the classroom does not have the capacity to sit more than 100 students. This is precisely what is happening in a heavy nucleus. Understand the fact, and I'm very sure that you've all heard of it: like charges repel each other, unlike charges attract each other. Heard of it, right? So all these protons are what? Protons are like charges. And all these protons are housed inside this very small nucleus. So inside this very small nucleus, you have all these protons which are just stacked together. So until a point, they are still able to manage and they overlook the problems that they are facing, the repulsion that they are facing. But then there will be a point when they will say enough is enough. Now we can't manage this anymore. The repulsion will be too strong. And this is where some of the particles will start coming out of the nucleus. So this is basically a premise for alpha decay. This is a premise for alpha decay, that after a point the number of particles is very high, and that's why the atom will not be good enough to sustain. All right, atom will not be good enough to sustain. So that is precisely what is happening in this particular scenario. All right, so alpha decay. So alpha decay, when is it happening? Whenever the number of protons is very high. This is when alpha decay will take place. Second one is beta decay. When is beta decay taking place? Beta decay is taking place when the number of protons is not equal to number of neutrons. Number of protons is not equal to number of neutrons. This is when beta decay happens. Now, this uh, you can say the asymmetry in the number can happen in a light element and can happen in a heavy element as well. So whether it's a lightweight atom or a heavyweight atom, in both the cases, beta decay might happen. So that's why light as well as heavy element. So understand the fact that alpha decay, it cannot happen in a light nucleus. Why? Because lighter nucleus will have a very strong nuclear force or very strong nuclear binding energy, and that will not let go of any proton or even neutron so easily. So that's why alpha decay generally will not be seen in any lightweight nuclei, because they are stable, they can manage. But in a heavy nucleus, when the repulsion starts to increase, this is where we'll see that alpha decay would take place. So overall, let's say this is what we would see with beta decay also. This is what we'll see in beta decay. The beta decay could happen in both the cases of a lightweight nucleus as well as a heavy nucleus. Now, how exactly? We are saying asymmetry. Asymmetry can happen in two ways. Either the number of protons is more and number of neutrons is less, or the number of protons is less and number of neutrons is more. So these are two cases in which this can happen. So if you look at the first case here, carbon 14 changes to nitrogen 14. Now, how would we represent carbon 14? We can represent carbon 14 something like this. Correct? And this is converting into nitrogen 14, which is something like this. Keep answering this. How many protons and neutrons in carbon 14? How many protons and neutrons in carbon 14? And how many in nitrogen? The representation will give you the answer. Yes. So some of you, I'm waiting for more answers. Wonderful, wonderful. Great. So as many of you have written here, this is correct, that you have 6 protons and 8 neutrons, whereas in case of nitrogen, this is 7 protons and 7 neutrons. So do you see that nitrogen will be stable? This is stable, correct? This is stable because number of protons and neutrons is same. So basically what happened here was that number of protons increased by 1 and number of neutrons decreased by 1 to provide this stability. Does this mean that a proton came from somewhere? Does this mean this proton came from somewhere? The answer is no. What basically happens is that one neutron converts into a proton. Don't ask me how. That's nuclear physics, which is completely out of our scope. But what basically happens is that one neutron converts into a proton. All right. So this is a kind of a rearrangement. It's a kind of a rearrangement that happens inside the nucleus itself. All right. So in this manner, what we see is that this is one way in which this conversion happens. Look at the second conversion. Second conversion is carbon 10 into boron 10. Now, what is carbon 10? How do we represent carbon 10? Like this. And this is converting into boron 10. This is converting into boron 10, which we can represent like this. Quickly, how many protons and neutrons for carbon as well as for boron? Yeah, some of you have answered. I'm waiting for more of you to answer this. Correct, correct. Wonderful. So in this case, again, See, carbon means 6 protons. That doesn't change. So 6 protons and 4 neutrons, which gets converted to 5 protons and 5 neutrons. So what's happening in this case? We see that number of protons here decreases by 1 and number of neutron here increases by 1. So basically this is again a rearrangement that is happening, and this again, because these two numbers are equal, this becomes stable. Correct? This also becomes stable. So to attain this stability, there is an internal rearrangement. This is an internal rearrangement. I'm going little above what is actually required for your examination, but just to give you the context, otherwise it will just become a factual lecture where there is no explanation for whatsoever. So that's why I'm going little beyond the syllabus just to set a context for what's happening here. All right. So this is basically what is happening in case of beta decay. So in beta decay, we see this particular restructuring. Then there is this gamma decay. Now gamma decay, there is no protons, neutrons being exchanged and being lost or being gained, etc. No. In case of beta decay, it's just about energy. What I mean is that typically after any alpha decay or after any beta decay, what we basically see is that the nucleus will be in an excited state. All right. So when I say excited state, it means that it has more energy than it should have. It has more energy than it should have. So we need to bring down that energy level. So whatever is the extra energy level, whatever is the extra energy that it has gained, we take away that extra energy. So that extra energy, we don't take it. I mean, there is an extra energy that is released by this nucleus so that it can become stable again. So for that, we see that this extra energy will be taken away in terms of gamma rays or in terms of gamma photons. So when a nucleus is in an excited state, spontaneously decays into ground state, a photon is emitted with energy equal to the difference in the two energy levels of the nucleus. This is called as gamma decay, right? So what we basically mean here is that when we say excited state, so excited state means that when it has more energy than required, than what is required or usual. All right, this is called as excited state. And ground state basically means that this is the required or usual energy. So required, so when it has required or the usual energy, it is called as ground state. And when it has more energy than what is required, it is called as excited state. So when a nucleus is in an excited state, it needs to lose energy, and this will be that extra amount of energy so that it can come back to its ground state, and that extra energy will be lost. And this is done by the uh, with the help of gamma rays. All right. So whenever an alpha or beta decay results in daughter nuclei in an excited state, we typically see that gamma rays are also emitted here. So in this manner, we see that this is particularly happening here. So if you see this, you have this excited state nucleus, which goes down to its relaxed state by releasing all the extra energy in terms of gamma photons, right? So these gamma photons, they have the extra energy. They have that extra energy. It's just like when you have, let's say, if you have a small child in the home, you'll see that always they are just jumping around, and then somebody will get angry, maybe one parent, and either scold them or maybe beat them, which should not be done actually, but they come back to the relaxed state. So something like this will happen when the photon, the gamma rays, the gamma radiations are taken away from this excited nucleus. It will come down to its relaxed state, and this is called as gamma decay. So in this manner, we see that this gamma decay takes place in this scenario. Now, overall, when we do the energy comparisons between alpha decay, beta decay, gamma decay, etc., you'll see that every one of these, they have different energy states, or they have different energy levels. So for example, alpha radiations, or alpha rays or alpha decay or alpha particle, all these things. So I'm just writing it out here because every one of these things basically mean the same thing. So whether you say alpha ray or alpha radiation or alpha particle or alpha decay, all these things essentially basically mean the same thing. So alpha radiations, they have the least amount of energy, that even if you have a thin sheet of paper, it will be able to stop the alpha rays. Then the beta radiations, they are little stronger, have more energy, so you need a thin sheet of metal to stop them. In case of X-rays and gamma rays, which have essentially the same amount of energy, you need a thick sheet of lead to stop them. And in case of neutrons, they can travel even further, can have more energy, and you need a thick sheet of concrete or steel to stop them. So that's why we need at least 15 centimeters thick concrete or steel so that you will be able to stop them. So that is how we see that there is this energy comparison between all these different types of particles or energy that is being released out of the nucleus. So in this manner, we understand that this is how the things take place. So overall, this defines basically what we are looking at. So when we discuss about nuclear energy, we understand that in case of nuclear energy, this is what is happening, that the energy that we have per nucleon, it basically differs, and that energy is what we call as the binding energy. So overall, when it comes to energy, what we understand is that when we have a nucleus, we see that inside the nucleus there are multiple different things which are happening here. Now, when it comes to these two concepts of what we had discussed in nuclear energy, of nuclear fission and nuclear fusion, try to understand what is happening in terms of nuclear fission and fusion. So first thing is nuclear fission. What we discussed about fission is that nuclear fission will happen when you have a heavy nucleus, correct? When you have something like uranium. When you have something like uranium, this will lead to nuclear fission. Now, what is happening in nuclear fission is that atomic nucleus breaks up into two or more major fragments with the emission of two or three neutrons. Correct? Nucleus breaks up into two or more major fragments with the emission of two or three neutrons. This is accompanied by release of energy in the form of gamma radiation and the kinetic energy of the emitted particles. This is called as nuclear fission. Try to understand it with the help of this particular picture. This is typically what we do in nuclear fission. First and foremost, we take uranium 235. Now, as we discussed about hydrogen, that hydrogen has various isotopes. Similarly, uranium also has various isotopes. We have uranium 233, we have uranium 235, uranium 236, uranium 238, uranium 239. So there are multiple different types of uranium. So we take uranium 235, and this uranium 235 will be bombarded with a neutron, meaning that we basically are throwing or bombarding a neutron towards this uranium 235. Now what happens, that this neutron, it goes and sticks to this uranium 235, and hence it becomes uranium 236, because 92 represents number of protons, 236 represents number of protons plus neutrons. So there is one extra neutron that has come up. That's why this 235 changes to uranium 236. Now this uranium 236 is very highly unstable. Uranium 236 is very unstable and is not able to sustain its shape, and it just breaks. All right, it breaks into two daughter nuclei, as you can see, into krypton and barium. It breaks into krypton and barium, and while breaking into krypton and barium, it releases three extra neutrons plus a lot of energy. So if you see this while breaking, basically you'll understand this, that this 92 got broken down into 56 plus 36, which is equal to 92, which is fine. This 236 became 92 plus 141, which is 233 plus 3. So this plus 3 that I have here, these are the three extra neutrons. These are the three extra neutrons. So this is basically how we see that there are three extra neutrons which are produced here. Now these three extra neutrons will not stop here. All right, these three extra neutrons will not stop here. So what will happen is that they will go further and bombard three more neutrons. Sorry, three more nuclei. All right, they will go and bombard three more nuclei, wherein we'll see that this will again produce three more nuclei, sorry, three more neutrons. So something like this happens, that there are these three neutrons again which have been produced. So then what happens? Again, you have these three extra neutrons forming in all these steps. So what happens next? This also will keep on releasing three extra neutrons while it goes and keeps, and it will keep on releasing more and more of energy, correct? So now this scenario is called as a chain reaction. This scenario is called as a chain reaction. So what is happening is that at each and every step, more and more energy is being produced. That first, let's say there was only one instance of energy being produced. Now this equivalent of three times from all these three nuclei. So if this, it was 1 joule, now 3 joule. Then from there 9, 27, 81, 243, 729. So it will just keep on increasing like this. So all of a sudden there is enormous amount of energy that you're producing here, and this is called as a chain reaction. Now this chain reaction, basically the energy that we are getting is in terms of the gamma rays plus the kinetic energy due to the movement of the particles, correct? Gamma rays and the kinetic energy, they are leading to this kind of an energy that is being released from here, and then extra amount of energy at each and every step, causing that chain reaction to take place. So this is what happens in nuclear fission. All right, this is what nuclear fission is, when this unstable nucleus is basically breaking down into two or more fragments while releasing a lot of energy. All right, this is basically what we see with nuclear fission. Now there is something that we need to understand. There are two basic problems that we see with nuclear fission. What are these problems? The first problem is something that we just saw, that there is an uncontrolled chain reaction, correct? There is a chain reaction that has been initiated here. We need to control this chain reaction. If we control this chain reaction, we produce electricity. If we don't control this chain reaction, atom bomb. So that can be a very slight difference between controlling and not controlling. If you are able to control, if you are actually controlling, then in that case you are producing or generating electricity from here. If you are not controlling this energy, then in that case it takes the direction of forming an atom bomb. And there can be a very small gap between something like this happening. So that's why there is this concept called as critical mass. There is this concept called as critical mass. So critical mass is that mass which we want to maintain so that you can control the chain reaction. All right, to control the chain reaction we need critical mass. Neither we can go above critical mass nor we can go below critical mass. If we are above critical mass, it means that the reaction is totally uncontrolled, and then it can very easily lead to some kind of a disaster. If the critical mass is less than what is required, the reaction, the chain reaction, will not be even set up perfectly, and very quickly we'll see that whatever energy was released, very quickly it just dies down. So that's why you cannot be above critical mass, you cannot be below critical mass. So critical mass is that mass of the fissile material that will help in undergoing continuous chain reaction. All right, so critical mass is the mass of the fissile material. Fissile means whatever can undergo fission. Of the fissile material Fissile meaning can undergo fission, at which sustained and controlled chain reaction can be set up. All right. So this is basically what we call as critical mass. Just to give you a context, in the entire calculation that we do for nuclear energy, there is this one factor that is K. So when this factor K is equal to 1, this is called as critical mass. All right. This is called as critical mass. When K is equal to 0.99, the reaction will basically stop quickly. And if the value of K is just 1.01, all right, even if it is 1.01, the rate of reaction, the rate of reaction, can you guess how much is the increase in the rate of reaction? By what factor does the rate of reaction increase? Just take a wild guess. No, no negative marking. Just take a wild guess. How much does the rate of reaction increase by? Okay, I'm getting some answers. Double, 10 times, okay. 50 times, 1 lakh times, okay. So the rate of reaction actually increases by 22,000 times. Rate of reaction increases by 22,000 times. So just imagine how much is the difference. From 1 you have increased it to 1.01, and this rate of reaction is increasing by 22,000 times. So just imagine the kind of destruction it can cause with a small amount of difference, right? So that is the problem. That is the problem. So K, so what is K? K is just a factor. You don't need to study K. I just wanted to give you the context of, because it's a big formula that we have for calculating nuclear fission or the energy through nuclear fission, where there is this one small concept in this formula. Don't go there, it's nuclear science. So but just imagine the kind of increase that happens in the energy if critical mass is not in if not maintained. So that's why we say that for any reactor to start working, it must reach criticality. So that criticality is nothing but maintaining that critical mass is called as criticality. So this is basically what will happen. This is the first problem that we need to solve, that our chain reaction to be should be controlled, should be sustainable, and then only it will be safe enough to use and produce electricity from here. All right. So this is basically the first part of the problem. Then let me tell you about another problem. And this another problem is basically the nature itself. When the mining of uranium is done, all right. So let's say if we have mined 100 grams of uranium, we extracted 100 grams of uranium from the uranium mines. From this, there are two natural uranium that we get. One is uranium 235 and the other one is uranium 238. Now, between uranium 235 and uranium 238, uranium 235 is said to be fissile, meaning that it can undergo fission. Actually, uranium 235 is the only natural fissile material. Uranium 235 is the only natural fissile material. I'm just writing it out, just a basic fact about uranium 235. It's the only naturally fissile material. Only naturally fissile material is uranium 235. Uranium 238 does not undergo fission. All right. So it is not fissile. Uranium 238 is not fissile. Now comes the problem. Out of these 100 grams, only 0.7 gram is uranium 235 and 99.3 grams is uranium 238. So what do we do? That this is something that we now can really not do anything about, that its nature, that this is what the fraction is, that only 0.7% of the fraction is uranium 235 and 99.3% of the fraction is uranium 238. So now what we next have to do is we try to increase this amount of uranium 235, and this increase in the amount is called as enrichment. This is something which is called as enrichment. And this kind of uranium 235 is called as enriched uranium. This kind of uranium is called as an enriched uranium. So enrichment is where from 0.7% of uranium 235 we go to 3 to 5% of uranium 235. So we increase the concentration of uranium 235 from 0.7% to 3 to 5%. Now, there can be a question in your mind that if we are convert it to 100%. Why are we taking this small measure of just converting it from 0.7 to just 3 to 5%? Why not 90%? Why not 100%? As you start to go beyond this 5%, as the enrichment goes beyond the 5% mark, we see that this uranium 235 starts to become unstable. It starts to become very unstable, and it has higher potential to go and to undergo uncontrolled nuclear chain reaction. So that's why there is a limit that is put internationally agreed, that if you are using it for civil purposes, if you are using it for electricity generation, then you do not go beyond 5% limit. If you go beyond 5% limit, it simply means that you are making an atom bomb. Recently, there was a news about US claiming that Iran now has almost 90%, 85% to 90% enrichment done. So if that happen, if that is true, it simply means that Iran is making atom bomb. So that's why the permissible limit for civil purposes for electricity generation is just 3 to 5%. And none of the countries, without informing the international arena, they should not actually be doing this kind of an enrichment. Otherwise, it simply means that they are secretly making an atom bomb. So that's why enrichment, although can be done beyond this as well, but if you do it beyond 3 to 5%, it simply means that you are preparing nuclear weapons and you are not going to use it for nuclear energy or electricity through nuclear energy. So that is basically what happens in this particular scenario, that we see that enrichment will be carried out so that you have better percentage of uranium 235 which is usable for electricity generation. So nuclear fission. So I'm just writing this point also here, that nuclear enrichment is only carried up to a certain limit, which is essentially just 3 to 5%. Beyond this, enrichment would lead to creation of nuclear weapons. All right. So that's why enrichment is a process which is very, very closely watched by everyone. Because if it is done beyond 3 to 5%, it simply means that you are making atom bomb and you're not actually going to use it for electricity generation. So that's why this is something that will be maintained by each and every country. So that's why there are these two problems that we need to solve when it comes to nuclear fission. That first thing, to maintain that critical mass, so that that critical mass can help in sustained and controlled chain reaction for electricity generation. and second because you have very small amount of nuclear, very small amount of this uranium 235. You want it to increase it to a certain level so that you can do better production with better efficiency with the same amount of uranium. But if you go beyond that, it simply means that atom bomb is being prepared by somebody. So this is what we have with regards to nuclear fission. Next up is nuclear fusion. Now, in case of nuclear fusion, what we see is that fusion means joining, meaning that there are two lightweight nuclear particles, or there are two lightweight nucleus which are now going to combine together so that they can increase, they can also release this energy. They'll also release this energy in this entire process. So as you see here, that deuterium and tritium, they are combining together to form helium while releasing a lot of energy. So if you see something like this, if you look at this equation, this is the equation that takes place inside the sun. So what is happening inside the sun is that first you have two normal hydrogen that is coming together, and these are combining to form deuterium. Now this deuterium combines with more of hydrogen to form helium 3. Now this helium 3 is highly unstable. This helium 3 is highly unstable. So this helium 3 will combine with more of itself to form helium 4. All right, to form helium 4, which is the stable helium. So ultimately, if you look at the entire reaction, what's happening basically is that hydrogen got converted into helium while releasing a lot of energy. All right, so hydrogen converting into helium while releasing a lot of energy. So this is a set of chain reaction that keeps on happening inside the sun, which releases enormous amount of energy. Now nuclear fusion packs a lot more energy than nuclear fission, but the problem with nuclear fusion is it's not an easy job to carry on with nuclear fusion, because nuclear fusion is not that easy to do, to carry out, and there are very specific conditions under which nuclear fusion is even possible. So fusion reactions that produce large amounts of energy can be created only by means of extremely intense heat. Such reactions are called as thermonuclear reactions. So that's why nuclear fusion, in other words, we also call it as thermonuclear reactions. So that's why we see that this is basically the reaction that will lead to the kind of energy that the sun has, which becomes the source of all the life forms that we have on the earth. And the same can also lead to making hydrogen bomb, which again is a nuclear weapon. Now in case of nuclear fusion, for the fusion to happen, it's very necessary that you bring these two nuclei very close to one another. Understand the problem. Remember the classroom problem that we had discussed, that you have a classroom where not only the weekend batch students but even the weekday batch students have come, and they also are sitting there, correct? So imagine the reverse of it, where you have one classroom where only one student is sitting. So how lucky that student is that there is one teacher assigned to that one student who is going to teach. So there is all the stability that that student needs. So why would that student even entertain somebody else? Because when the student is getting a private tuition from one faculty, right? So in this particular case, what's happening is that this hydrogen is stable, right? In case of uranium, in nuclear fission, uranium was very highly unstable, but in case of hydrogen it is stable, so it does not really need to do anything. So that's why you will have to make the effort for it to join forces with some other element, or to join forces with another hydrogen. So then in that case, we have to make it happen artificially by bringing these two particles, or these two nuclei very close to one another, so that the nuclear forces can be activated inside them. But that's not easy. It's not that you'll just hold these two nuclei of hydrogen and you'll just bring it together and wow, this nuclear fusion happens. Unfortunately, things are not that simple. You need very specific conditions under which this can be done, and these specific conditions are extremely high temperature, extremely high temperature, extremely high pressure, and extremely strong magnetic field. So these are three specific conditions under which we see that in the sun they have these conditions that lead to nuclear fusion taking place there. Otherwise, in the absence of these conditions, nuclear fusion would not have taken place even inside the sun. So, if we want to produce electricity through nuclear fusion tomorrow, if that is the future that we are looking for, we will have to replicate these conditions. Correct? We'll have to replicate these conditions so that we can produce electricity with the help of nuclear fusion. So this is precisely what we try to do with nuclear fusion. There are two approaches that we use. One is called as magnetic confinement and the other one is called as inertial confinement. All right, magnetic confinement and inertial confinement. Magnetic confinement is when you are using very strong magnetic fields to confine the plasma, meaning that very strong magnetic fields are being used so that these two plasma, or rather these two, let's say, hydrogen particles, they can be brought very close to one another so that they can fuse together, so that nuclear fusion can occur between the two. So very strong magnetic field is being used here, and this basically is done in a toroidal form. So we have a toroidal shaped magnetic field. Toroidal shaped magnetic field. Do you know what toroidal shape is like? It's, you can imagine like a tire or a donut. All right, a better example, a donut. So if you have eaten a donut, the shape that the donut has, that it is round and it has a gap in the middle, that is called as the toroidal shape. All right, so there is this magnetic field in the toroidal shape that we produce, and then inside this, the gap that you have in the middle, just similar to, as I said, that imagine a tire also, where you have a gap in the middle, that is where you have the plasma, and you are surrounding it with very strong magnetic field, and this is something that can lead to nuclear fusion. So this basically is what we try with magnetic confinement. Then the second one is inertial confinement, and in case of inertial confinement, we use very strong, very powerful laser or ion beams. Laser or ion beams, and with the help of these powerful laser and ion beams, we see that inertial confinement is done. So what we basically do is, with the help of these strong lasers, we try to force these two hydrogen nuclei to come together, to come very close to one another, so that the nuclear fusion can be activated in this particular scenario. So that's why these are two approaches that we are using to experiment with nuclear fusion. Now, out of these, the first one, that is magnetic confinement, is being used in ITER, International Thermonuclear Experimental Reactor. Magnetic confinement is being used here to produce energy. So we have been working here. So if you look at this plant, this is a setup that we have in France. And in France, this is a setup that is basically working on all these aspects of nuclear energy to use magnetic confinement to produce nuclear fusion. Experimentally, we have succeeded. All right, experimentally we have succeeded, but we don't have the kind of success that we need for it to be replicated at a commercial scale. Correct, to be replicated at a commercial scale. So that's why we see that this is a large scale scientific experiment that aims to demonstrate that it is possible to produce commercial energy from fusion. So in this manner, we'll try to produce fusion based energy maybe in the future. Now, what we see is that it initially started with the former Soviet Union, the US, European Union, and Japan. And later on, India, China, and South Korea, these three countries also joined. So right now you have these 7 member countries which are a part of the International Thermonuclear Experimental Reactor, and all these countries together, they are basically working. They are basically working on this particular project. right? So this is basically what we do at ITER, where we are using this magnetic confinement. Now, when it comes to, okay, so this is also called as tokamak. Just remember this word tokamak. No need to go again into the details of what it is, because just in case tokamak, remember related to fusion. Now, the second one is inertial confinement. Now, when we say inertial confinement, recently, by recently I mean December 2022, there was a news that there is a big breakthrough that has happened in the field of nuclear fusion. That nuclear fusion now has a very big breakthrough. And this big breakthrough had actually come through nuclear confinement, sorry, inertial confinement. And if I tell you what this big breakthrough was, you will say that why is it even a breakthrough? So, so let me tell you what the breakthrough was. So until now, the problem with nuclear fusion for us has been that the energy that we have produced, and experimentally we have succeeded, that we have been able to produce nuclear fusion based electricity. The problem that we have is that we use more energy than what we get. Remember what we had discussed in case of shale presence in India, that although we found sources of shale in India, but extraction will need more energy than the energy that we will get out of these shale sources. So commercially not viable. Same is the scenario when it comes to nuclear fusion. Experimentally, we have succeeded, but we have wasted a lot more energy than whatever peanuts we get out of it. So that is the basic problem. Now, the breakthrough was that for the first time, using inertial confinement, we have been able to produce more energy than we consumed in the operation. This is a breakthrough. All right, so a recent breakthrough, here has been, for the first time, we have succeeded in generating more energy than we consume in operation. This was done with inertial confinement. Right. So with the help of inertial confinement, for the first time, we have been able to produce more energy than we consume in the operation. That's why we are saying that it's a breakthrough. Because until now, although experimentally we have been able to use nuclear fusion for electricity generation, but that has happened at a very, very small scale, which is not really relevant, because anyway, we are wasting more energy than that. And this energy was also, it was not that it was big amount of or enormous amount of energy, but it was good enough to boil maybe just a few kettles of water. That's it. So that was the extra energy. But at least for the first time, we could produce extra energy. So that's why we are saying that this was a recent breakthrough in nuclear fusion. Now, when it comes to nuclear fusion, there are certain advantages that nuclear fusion has. So just try to understand what are these advantages. So first, it produces abundant amount of energy. That this can give us much more amount of energy than any other source. And that's why if we succeed, if we get a commercial success in case of nuclear fusion, forget about any other source of energy. Our chapter will shrink and we'll only be studying about nuclear fusion, because it will make every other source of energy irrelevant, because with a very small amount of fuel we'll be able to produce enormous amount of energy. Just imagine the sun. Just imagine the sun, that the sun, at the core, the energy, the reactions that are happening, It is controlling the heat and the energy of almost the entire solar system, at least the inner solar system. So that's why abundant amount of energy. Then the sustainability factor, that we will be able to use this energy for a very long time, and it's not that we will basically will not be confined for a very short period. So that's why in a manner you can say, that's why, if you remember, I had told that if fusion becomes possible, nuclear energy is then renewable, correct? So that is why sustainability, that if we get commercial success with fusion, nuclear energy essentially becomes renewable. All right. So that's the thing. Then again, of course, no carbon dioxide. There is nothing in this operation that would produce carbon dioxide. So that's why it becomes a very clean source of energy as well. Then after that, no long-lived radioactive waste. This is a problem with nuclear fission. And we'll discuss in tomorrow's class why exactly it is a problem with fission. But we understand that what basically happens is that the radioactive waste that are produced by nuclear fission operations, they can be in the environment, they can live in the environment for a very long time. I mean, some of these fission products can live in the environment for 10,000 odd years. So just imagine. So that's why no long lived radioactive waste. So that is something which is very important, because the radioactive waste, so because what happens is that the waste is tritium water, right? The waste is tritium water, that is T2O, which is, and this quickly decays, quickly within seconds converts to normal water, that is H2O. So that's why what happens is that the radioactive waste, even being produced, is so unstable that it quickly converts into normal water, that is H2O. So that's why we don't even have a problem with this kind of a radioactive waste. So that's why no long-lived radioactive waste is a very, very important uh, uh, property to have. Then limited risk of proliferation. So what do we mean by proliferation? It means that it basically means weaponization. It means weaponization. Understand, we are saying limited risk. All right. We are not saying no risk. We are saying limited risk. Why limited risk? Because in the operation of nuclear fission, the uranium based power plants, the byproducts that we get from there, for example, plutonium can be used in making nuclear weapons. All right. So in the same operation where you are producing electricity, the output of the same operation can also help us or rather manufacture atom bombs or nuclear weapons, plutonium basically. But in case of hydrogen based fusion, that's not the case, because even if you think of hydrogen bomb, the process to produce hydrogen bomb is completely different, and it's not an outcome directly out of this kind of a process. So that's why the risk of proliferation is pretty less. So that's why this also becomes one of the very important points. So I'm just writing out fission here, that in fission byproduct is plutonium, which can be used to make nuclear weapons. So that is not the case when it comes to hydrogen based fusion. So that's another advantage that nuclear fusion has. Then no risk of meltdown. So meltdown is nothing but the accidents that can happen in these cases. So accidents about what we have seen in Japan, what we have seen in the 3 Mile Island in the US, and the most famously or infamously what happened in Chernobyl. So Chernobyl or Japan or US, in all these cases we see that these kind of meltdowns have happened with nuclear fission. But again, with nuclear fusion, that risk of meltdown is not there. Why? The reason is that you need very extreme conditions for nuclear fusion to even happen. Extremely high temperature, extremely high pressure, extremely strong magnetic fields, extremely strong laser beams. So unless you have these conditions, nuclear fusion can't happen, right? Nuclear fusion can't happen. So as soon as you lose one of these conditions, the reaction will stop then and there. So that's why risk of meltdown not there. So why risk of meltdown is not there? Because conditions for fusion are extreme. If these conditions are lost, if these conditions are lost, the reaction quickly stops. So that's why there is no risk of meltdown when it comes to nuclear fusion. And then lastly, the cost. Because once we are able to commercialize it, of course, we are using hydrogen, we can reuse hydrogen, and with small amount of hydrogen, we'll be able to get huge amount of energy. So that's why the cost will also be brought down when nuclear fusion becomes possible. So that's why in all these scenarios, we understand that nuclear fusion will have all these advantages, and hence nuclear fusion is what we are looking for, right? This is why nuclear fusion and why we are spending so much of money on nuclear fusion. The problem is that implementation of nuclear fusion is not that easy. There's a joke that goes around that if you go and ask a nuclear scientist that when is it that we'll start using nuclear fusion, they'll say 20 years from now. That nuclear fusion is 20 years away, and for the last 60 years it has remained 20 years away. I mean, I don't want to joke on this because it's such a complex technology to function with. So that's why, of course, it's not that easy. But this is, I mean, in the scientific world, this is a joke that goes around that ask a scientist about nuclear fusion and they'll tell you 20 years. That in next 20 years, nuclear fusion will be a reality. So, but these are the advantages, and this is the reason why we are emphasizing so much on nuclear fusion. And even though we haven't been able to be successful, we still keep on spending on nuclear fusion because we know that once we are able to crack this technology, then after that we are not going to look backward, and we'll always have this nuclear fusion that will take care of every needs that we have altogether. So that's why all these advantages. Look at this question. This question was asked in your 2016 paper. India is an important member of the International Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? This was the question. I'm launching the poll for you. Please mark your answers and let's have a discussion on this. A simple question. Let's end well. Give me correct answers. All right. I hope that you've read the question. I'm giving you 30 seconds. Please mark the answers. Hmm. So 57% of you have given the correct answer, that is D. And then after that, there are 29% of you who have fallen into a trap, that is C. All right. So India is an important member of the International Thermonuclear Experimental Reactor. If this experiment succeeds, what is the immediate advantage for India? First, it can use thorium in place of uranium for power generation. Now, which kind of nuclear reaction is ITER related to? Nuclear fusion. We just discussed about this. That India became one of the 7 members of ITER using magnetic confinement approach to use nuclear fusion commercially. So uranium is used in nuclear fission. So that's why nothing to do with it. So this is wrong. It can attain a global role in satellite navigation. I mean, this is nothing to do with satellite navigation at all. We did not discuss anything regarding this. It can drastically improve the efficiency of the fission reactors. No, they shouldn't have been marked. We are simply talking about fusion. So there is no point about increasing the efficiency of fission reactors. It's completely about fusion reactors. So correct answer, it can build fusion reactors for power generation. This is the future that we want, and that is the whole idea why we are spending so much on an experiment like ITER. All right, so this is basically what we see with nuclear fusion. Now, if you have any questions with regards to whatever we have discussed with regards to nuclear fission and nuclear fusion, there's also an option of live call if you want. This option is also there. So if you directly want to ask a question, you are most welcome to do that. Because I don't want to proceed here because this next topic is probably a half an hour topic, and comfortably we can start tomorrow when we come back at 10 o'clock. So we'll not proceed further. So everything that we have discussed, please let me know. If you want, we can. Uh, so if you have any question, please let me know. Otherwise, see, this last part that we have discussed after 6 o'clock, it's a little typical part, can be a little difficult for you to understand at times. So please make sure that you actually uh, go and revise all these things that we have discussed. What is MEV? MEV stands for mega electron volt. So electron volt is also one of the ways in which we measure energy. So MEV stands for mega electron volt. And often when it comes to nuclear energy, we basically do these calculations in mega electron volts. Did not understand ITER. ITER is nothing. ITER is an experiment where we are trying to use nuclear fusion. We are trying to succeed with nuclear fusion using magnetic confinement. Now, magnetic confinement is nothing but you can think of the sun, that how the core of the sun is surrounded by the strong magnetic field, which makes sure that the fusion material does not get out of it and fusion can happen. So we are trying to create a similar sun like situation by having a magnetic field all across, and the hydrogen conversion into helium is happening in this particular scenario. So today fission is used for electricity production. Yes, absolutely. Today it's only and only nuclear fission that we are using in the nuclear reactors. And this is precisely what we will start with in tomorrow's class, understanding how these nuclear reactors work. What is a neutrino? Neutrino, we had discussed in the last class that neutrino basically is a particle which has a very, very small mass and zero charge. I mean, it is neutral charge wise, and mass wise, it is very lightweight, lighter than even protons and electrons. So that's why it is almost undetectable, because it is chargeless and almost massless particles. And there are many natural processes in the entire universe that can lead to the production of these neutrinos. For example, we had discussed about supernova in the last class. So these supernova are the biggest source of neutrinos in the universe. Plus, even nuclear reactions like nuclear fission and nuclear fusion also can lead to the production of neutrinos. What happened in Chernobyl? So in Chernobyl, basically what happened is that the the pressure that they have there, the pressure vessels were not basically functioning well, and because of which the the k value that we had discussed, the k value had started to increase. So they had seen it, they thought that they would be able to control it, and they kept on running the operation. They should have stopped the operation there. They had the confidence and they thought that their calculations were right, and that they'll be able to bring it down and they'll be able to control the chain reaction. But unfortunately, it started going to a level where they could not control the chain reaction, and this led to the disaster. All right, so I think I have taken the questions that all of you had. Right. So let's end the session here. We'll meet back tomorrow. We'll start with nuclear reactors. We'll finish this chapter of nuclear energy in the first hour or so. And then after that, we'll proceed to our next chapter, that is biotechnology. So in tomorrow's class, we'll finish nuclear technology, we'll start biotechnology, and then towards the end of the class, we'll take up nanotechnology next. So these are three chapters that we'll do: nuclear energy, completed; biotechnology, nanotechnology. If the time permits, then robotics and artificial intelligence towards the end of the class in tomorrow's session. All right. So with this, I end the session for today. Thank you very much for joining. Thank you very much for being patient and listening through the lecture. Please go back, revise if possible. Otherwise, at least at the end of tomorrow's class, please revise everything. Thank you.